So hi everyone, and thanks again for coming to our first meetup. And this presentation is going to be technical, and the purpose is to actually kind of bind or make a technical reference to what Alex has been talking before. My name is Lukáš Kolísko. I'm also member of blockchain R&D here at CA. And actually, when I was thinking about the content of the presentation, initially I wanted to jump right into some more technical details about consensus, their different variations, and so on. But attending meetups, talking to the people, I realized that there is a lot of misconception and misunderstanding about some basic building blocks and concepts around the blockchain. So I decided actually to include them in my presentation too. I would like to ask if to leave the potential question to the end of my presentation, but to still to keep it semi-interactive. If I will see that you raise both hands, I will skip to the next slide, because I know there is food break after my talk, so my presentation could be hijacked this way. So that's why I would need at least 51%. So what are the main components of the blockchain? So it's distributed ledger, blockchain network, smart contracts, and consensus. You heard about them more from the business perspective in Alex's presentation, and now I'm going to drill down in the technical details. So I hope the first slide immediately confirms that this is going to be technical presentation. So here actually I hope that at least the picture on the left upside is familiar to you. So by the way, quick poll, is there any blockchain developer here? One, okay. So the blockchain on the high level is really chain of the blocks. That's how it got its name. And every block in its content, I think, does it have, I will not write, rather. Basically, every block contains a list of transactions, and these transactions can be either money transfers, or this can be any other information like transfers of the assets. And part of the block is something called a header. And this is actually how, and the header of itself contains something called a hash. What hash is, it's a function that is able to convert a set of data into a fixed signature. And basically you are able, just having this small signature, to verify that the data has not been tampered, has not been changed. But it's virtually impossible to get back from the hash to the original data. It's used a lot in cryptography. And that's actually one of the tricks how the blockchain ensures that it's secure and immutable. Every block contains a hash of its predecessor. So this creates a list, a linked list of the blocks. And if you would like to change, for example, block in the middle of the blockchain, what you would have to do is actually recalculate hashes of all the blocks till the tip of the blockchain. So this would still be easy. And there is one of the misunderstandings with the basic data structure of the blockchain. This is ensuring the integrity, but itself it would not prevent like immutability. So there could not be really a party that would create a parallel chain. There is a trick inside, and it's part of the consensus I'm going to talk about, and that's the nonce. So the header itself contains a number, and that's the number that actually all these miners you are hearing about in a big Bitcoin news, they are actually trying to find the correct number, because the number of the hash number is not an arbitrary number, but has to have certain patterns. So it's actually hard to find this nonce, and in a Bitcoin network it takes on average, it's set to be on average to take 10 minutes. So this is actually, the blockchain itself is guarded by all the energy that would need to be spent. So you create, if you do modification, to basically rebuild a parallel chain with your potential malicious transaction. What's also important to say that the chain of the blocks is not the only possibility how blockchain solutions works. Therefore, we talk it's better to use actually distributed ledger terminology, because for example IOTA, which is one of the public blockchains that's focusing on IoT devices and therefore built for like millions of devices connected, and actually now getting a lot of attention as it's being investigated, it's being used by for prototype by BMW, Mercedes and a lot of other companies. It's actually using directed acyclic graph. So you do not have a simple chain like in the blockchain case, but you have a complete graph. And you also do not work on the level of the blocks, but these are separate transactions. So another thing, then you may ask why we talk about the blockchain, why we do not have transaction chain. And that's because with actually finalizing of every block, appending it to ledger, whole network has to agree, and there is a lot of overhead connected to that. So if we would work just on a level of the single transaction, the overhead would be unbearable. Therefore, we put transactions to the block, and this speeds up the processing and increases the transaction throughput. Therefore, if you are familiar with the cryptocurrencies here, as I have seen few hands up, you see there's the difference, for example, between the blockchain, between Bitcoin, that is 1 megabyte block, and Litecoin, and potentially different other implementations. So that's the reason, that's one of the reasons. Actually, it has a lot of other consequences, but that's one of the main reasons. Blockchain network, I think that's kind of the clear again. It's just really a network of computers or processes that are running certain software that connects to the blockchain network and does their certain role. And each of these nodes, or most majority of the nodes, are holding copy of the ledger. A lot of the articles contain the picture above. So does anyone seen that picture already? Okay, some have seen. Actually, the picture itself is from 1962, right? So it's from On Distributed Communication Networks paper by Barant. So actually we are there talking about the technology like in 20th century I would be talking about the steam machine, because most of the things are actually from the 60s and 70s and developed by Lamport and others. So nothing really new. And this picture can be confusing because most of the services today you are accessing are actually centralized distributed. So what now, right? You talk to Facebook, Google, whatever, these are centralized distributed, so the picture doesn't give clear answer. Also, I was showing the picture to my friend and he told me, okay, but the decentralized picture is wrong because you have everything goes through a single node. It's not a network topology picture. It actually talks how the process is dispersed into the network. Therefore, I think it's much better if you would like to understand and learn what's the difference, this picture from Windley, where horizontally you have on one side centralized systems and on the other side decentralized. And it's not about location. It's actually, it's about the control. So in a centralized case, it means there is a single master process that actually tells everyone else what to do. In a decentralized case, they operate independently, mainly on their local state. On the vertical axis, this is about location. It can be, or collocation, it can be like physical or logical, but in a distributed ledger, through resiliency, we would like a physical distribution. So that's why actually everyone is striving to have distributed, decentralized ledger. And you can also see what centralized distributed means. And the last introductory slide is about the smart contracts. So Alex already mentioned that it should be kind of invented as a digital counterpart to a legal contract. And there is somehow a lot of confusion what it really means. And for developers, it's really nothing else than just a piece of code or script that's running on a blockchain. It doesn't have to be deployed directly on a blockchain, but it can be running aside. There are different solutions, and its purpose is to implement the business rules. As you in current architectures, you have some layer that's implementing the business rules. That basically what a smart contract is doing. To give a real-life example, if you are really with the hype, then you will not go to a attorney lawyer to prepare a last will for you, but you will write it for Ethereum in Solidity, then deploy it to the Ethereum public blockchain, and well, when the time comes and the Reaper sends your final transaction, then the smart contract will be executed, and whatever was in your last Solidity will happen. So that's kind of a real life example. There are a lot of disputes around this. Of course, it's not so easy actually to write real laws in a form of code, but just to understand the overall concept, why it got the smart contract name. And now actually getting to the core part of my presentation, and that's consensus. This is from, I think, the fair fair three I've been talking, you probably heard about them. The consensus is actually the most important part, and that was the breakthrough that Bitcoin has brought. And what you have is basically a set of, you have a distributed, decentralized system, and you need to have a process that all these different members, potentially not trusting each other, agree collectively on that ledger. And actually, the Bitcoin itself, that was the biggest breakthrough, technical breakthrough it brought, because a lot of these consensus algorithms, as I mentioned, they are from the last century. This has been investigated, but then there was not much interest in that, and Bitcoin actually revived that interest and was able to implement it on internet scale. To explain what are the issues there, that it's not so simple to come to an agreement, there is the Byzantine generals problem story. And actually, you can imagine there is a city and it's surrounded by multiple Byzantine armies. And these armies are led by different generals. And what they have to do in order to succeed, they need to have a consensus when they are going to attack the city or if they are going to retreat. If they do not come to a consensus, then they would be defeated. And this problem can have multiple layers. First, if they would just light a fire before the attack, the guards of the city would see it. So not just exchanging the messages, it's not so simple. Second, if they send a messenger, it can be captured, replaced with other messengers sending different message, and so on and so on. This can be potential even on internet scale solved with modern cryptography. But it has another layer, and this is that some of these can be actually traitors. They might send different messages to different generals. They might agree they are going to attack, but they would retreat, and this would mean defeat of the rest of the generals. So if you build if you build something like a Bitcoin on internet scale, you actually have to be able to be proof against these issues. It's hard to solve it like completely, therefore you have something like practical Byzantine fault tolerance, which is you have guarantee up to a certain number of the traitors in the network. And it doesn't mean like a traitor, someone that intentionally does a malicious behavior. It can be just an issue like an error in the system. There is actually a great paper from NASA that talks about the issues in real-world systems, like during the testing of nuclear submarines. They actually find out similar problems. Yeah. Yes, the nodes that participate in the consensus. Yes, in a case, if we connect it with Bitcoin and cryptocurrencies, what's the issue is there is double spending, right? That you have certain amounts in your wallet, and you would send basically all the funds to two different parties. And that's the malicious behavior, and you actually have to solve it in a way that really the network is able to capture it. So that's probably the most comprehensible example of a malicious behavior that actually Bitcoin managed to solve on such large scale. This is maybe too technical for the audience, but just the order execute architecture. The majority of the blockchains today are actually following this architecture, and what happens there is that clients are sending transactions, be it literally money transactions, asset transfer transactions, whatever, state changing transactions. And there is some process I've been talking before, the consensus that ensures there is a common ordering of the transaction and agreement was going to be next finalized block. And when this happens, this block is sent, broadcasted through the network, and then what all the nodes are doing are basically executing one by one in serial fashion the transactions that are in the block. And this has few issues. First one is that, of course, it limits the throughput, because they have to execute, every node has to execute it. They do it in parallel, but they have to execute it in serial fashion, which is not a problem for simple smart contracts, but as the smart contracts are getting more complex or might go to external services to check some conditions, then it slows down the network. Second one is actually this is prone to denial of service attack, because in Ethereum, in Bitcoin, it's the Bitcoin script is designed in a way that prevents this, but in Ethereum you can create a smart contract with infinite loops. So what would happen, because the smart contract executes literally on every node, that it would bring the whole network to the halt. Therefore, the blockchain have to come with protection to this, and in Ethereum case, this is the concept of the gas, where you are basically paying for every instruction, and as you do not have infinite amount of the money, then it's not possible to simply put the network to halt. The third, not so visible one, is also with the determinism, because it's executed on all the nodes, and if the same code executed on different nodes would end up in with different result, it would mean that actually the network desynchronized and basically falls apart, and this actually prevents why you see these domain-specific languages like Solidity, Serpent, or whatever are developed, because they actually need this determinism. In general purpose languages, and I'm not talking about JavaScript now, there are a lot of constructs that are prone to non-determinism, right? You have multi-threading, even in Golang, just iteration over the map can be non-deterministic. Therefore, actually, what Hyperledger did was come with completely different architecture, where it split the phase and made them available through separate components. So what is happening there is that someone sends a transaction to a network, and it arrives to a specialized nodes that do execute the smart contract, but they do not update the state. They just capture what has been written and what has been read from it, and check, of course, the correctness, and they then return it back to client. And client then sends it directly to another component that's running independently, and it's called orderer. And what it does, it orders these it's called read-write set, basically contains list of read operation, write operation, along with the versioning of the data, and just does the ordering. And when the consensus is reached, it's sent to the nodes to update their state. And they do not execute smart contracts. They just apply the read-write set and potentially check for the conflicts. So the smart contracts in this architecture can be executed in parallel, or you achieve much better parallelism, and also it's much more friendly for general purpose languages, because the non-determinism is captured in the first phase. It's much more pluggable for different consensus algorithms, and it allows a higher level of the confidentiality, which is important for the business use cases, because in the upper case, basically all the nodes are doing the execution and have insight, while there you can limit it to specific nodes and partition the network. So finally, we are getting to different consensus types. For the purpose, you can do various topology or split them in different classes. For the purpose of this presentation, I actually went with the lottery versus voting based. I think lottery based, most of you probably are familiar with the proof of work. That's the lottery based. And how it works is that you have some process, a lottery. In case of the proof of work, basically miners, as I mentioned in the first slide, are racing to first be first that find the correct number that generates correct hash for the previous block, and when they achieve that, they seal the block and send it to the network. So the advantage is that it scales really well. The disadvantage is that actually it can happen that there are multiple winners in the network, and this leads to actually forks in the network. There is rule how to resolve this issue. In a proof of work, it's typically that you pick the chain there is the most energy spent. Basically, the longest chain is going to be the new trunk. So this is the scalability, is the strong part. The time to finality, where finality means, as in a blockchain, actually you have to wait for 1 hour for 6 blocks to know that the that the block that contains your transaction is finalized, and still it's just a probabilistic measure. Another one that falls into this category is proof of stake, and to explain it really on a high level is that while in the proof of work case, basically what miners do is they bet the energy they are burning in their mining machines in order to get certain probability to win the race and forge the block, and therefore gain the profit from the Coinbase transaction, that fixed amount of Bitcoin that's given to the miner for every new block that he mines, and also the fees for that are connected to the transaction. In a proof of stake, this probability is proportional to your stake in the network. Basically, how many tokens you own in the network. So that's a general idea behind proof of stake. It has also, so it's more direct, I would say, economic model compared to proof of work. There are a lot of variations of proof of stake, delegate proof of stake, and so on. But that's the overall idea. If you are interested, we can talk later about different variants. The voting base, these are actually preferred in the private and permission blockchains, and it's because they actually are able to reach the finality, so you are sure that the transaction is not going to revert it basically virtually immediately, and it's because the consensus there happen in the way that the members of the network, the nodes, basically vote for a block, and if there is a majority achieved, then the block is considered as sealed and appended to the blockchain. And there is fixed process who is forging new block. It can be like external component, or it's not, or there is deterministic process who is forging new block. So the advantage is finality, disadvantage is actually scalability, because through the consensus they have to exchange more information, therefore it's much more attached to the underlying network properties like latency and bandwidth. So it may not work as great as the proof of work on internet scale, where you have unpredictable bandwidth, unpredictable latencies, and so on. Therefore, they are preferred for the private permission blockchain, and also thanks to the scalability, thanks to immediate finality. These are typically different variations of that implementing the Byzantine fault tolerance. Also, the proof of work and proof of stake has to be Byzantine fault tolerant, as they are used in public blockchains, or their implementation, for example, in Ethereum Casper or in Bitcoin Core and other variations. They need to be resistant to these attacks. So with all this together, hopefully now we can answer the question, what's the difference between the public, private, and permission blockchain? So if I would like to be really in a short, is basically who can access, who can join the network, and who can do modifications to the ledger in a public, anyone, basically in a private permissioned is restricted. But the answer is not so I think that this answer does not have so much value, and also it's not I would say precise. So I try to put together this diagram where on a vertical axis is actually the anonymity, or to be precise, pseudo-anonymity of the validators. So validators are the ones that are actually ensuring that the transactions in the blocks and blocks themselves are valid according to rules in the network. And on the vertical axis is actually how much trust is given to these entities. So for the Bitcoin or current Ethereum, they use proof of work, which it's permissionless, so means anyone can, it's open, anyone can join, and it's public, of course. The scalability is good. The token for the scheme is needed. You need for these some incentive to actually get miners into network, and these are that are securing the network. If you wouldn't have miners there, then the Bitcoin wouldn't be secure. And actually you see this behavior on the test nets, where they are not the miners are not incentivized by real money, so the attacks are there happening normally. So really, that's not really the cryptography and all what I've been talking before. It, especially in case of the proof of work, it needs to be secured by the miners, and basically at the end of the day by all the money these miners are burning. And the finality, it's slow, right? You need to wait 1 hour, 6 block, and it's still, you have to keep in mind it's probabilistic. Just the probability is so low that you can consider it as finalized. The proof of stake is much better and has been invented especially to address the issue with proof of work not being so eco-friendly. It scales much better, it's much faster, so there is not like 10 transactions per second with majority or proof of work or in that level. So it's getting on a higher numbers. Still the finality, it's again, it's much better, but you still need a token, and this is not usually good for business case scenarios, right? You do not want your supply chain to disperse token, and then everyone would be paying some virtual token for the operation. There are use cases where it makes sense even for the private blockchains, like some license management or whatever. But in general, mostly, I would say mostly what we know and talking to the customers and from the use cases, it's not the case. So therefore, there is actually the other, in the other quadrant, you see there is a permissionless public or consortium. Well, what are there is, for example, the Stellar or Ripple, and you see these are being adopted by the banks because they still allow like open system where the different members of the consortium can join. They are actually, they scale well, they are fast, and the finality is they're immediate. So that's important for majority of the use cases. You don't want to have a supply chain where you would wait half a day till you can be sure that the transaction is final and cannot be reversed and orphaned and get back to some mempool. And these actually, some of them, of course, implement tokens, but it's not necessary for that scheme. And the last one is the permission private. So these are really run in between. They are still running within a consortium, but they are not open. And what's important there is that actually identity of the members is known. So example from the Ethereum proof of authority algorithm can fall here. There are different implementations of BFT. And basically, the only kind of their weakness is usually with the scalability, because if you have really huge number of nodes, they have to, during the consensus, exchange lot of information. So this can slow down the consensus. And as we are on the Hyperledger meetup, I thought that it would be good also to talk about the Hyperledger project quickly. So we are actually working and using Hyperledger Fabric, but there are multiple other projects under the Hyperledger umbrella, like Hyperledger Sawtooth by Intel that implements special consensus algorithm called proof of elapsed time, Hyperledger Burrow that has EVM EVM compliant machine to allow permission blockchain, Indy for identity management, and so on. There is also ecosystem of tools, and what I would say is a big advantage for using Hyperledger Fabric, that it's really well documented. There is industry support for that. It's actually a flagship for the IBM as their go-to solution, and it provides you with all the tools that you need to build a permission blockchain. It's full open source, so you do not need to use any proprietary service or the components. You are able just with that. You can use Golang, JavaScript, Java to implement smart contracts. So that's where we are looking. For the business cases, as we are really here want to focus on blockchain and the business, there are other contenders like Ethereum that's backed by Enterprise Ethereum Alliance. That is, I would say, the rule of thumb would be there to go if you need a token, if you are considering public blockchain, but even the performance is not there. It's supported, for example, by Microsoft with Microsoft Cocoa, and the performance there, what they are claiming is 1500 transactions per second. For the Hyperledger with the current version, the latest numbers I think were 3,500 transactions per second in their last white paper. It depends on a lot of parameters. But what I wanted to say, and what is usually complained and seen as a weakness of blockchain solutions, is the performance. But the truth is that we are incrementally actually getting there and getting slowly to the ballpark where, for example, what Visa requires and talks about 100,000 transactions per second. So these solutions are actually getting close. There are even other that now claim to be on 70 or 80,000 transactions per second. So it's just a matter of time, and it's a long time where we will be, where the blockchain will be ready really to high transaction throughput sites that are needed for credit card transactions and so on. So that's all from me. You can follow me on Twitter. I try to write articles on a blockchain topic, also on Medium. So if there are any questions. Thank you very much.